Welcome to the More Runtime Options talk. You can view this talk after you go through the few basic lectures, such as the talk on running the WRF model. It may also be helpful if you have gone through talks on WRF dynamics, physics, and the registry. Some content in this talk may depend on the knowledge from those lectures. In any case, write down the questions you have while listening to the talk so that we can discuss them at the tutorial. This talk will cover more model options we can set at runtime. Other options have been covered in talks like running the WRF model, nesting, model physics, and dynamics. This is mostly for our information only. We may find some of these are useful to us in our future research work. The options we're going to cover are listed here. In parentheses, I include the namelist name where the option is defined, wherever it is possible. In general, one can find the information in the registry file. These options are also documented in the user guide, so wherever it is relevant, we will point out the reference. Most of the namelists we have talked about so far are the namelist records listed here. There are other namelist records for special applications, such as those listed here. For example, if you've gone through the WRF nudging talk, the relevant namelists are defined in namelist FDDA. We are going to cover some of this in this talk, and also namelists we have not mentioned previously in other namelist records. If you need to use any of these namelists, find them from the file examples.namelist in the test emreal directory. This slide and the next show options we can use to do a better vertical interpolation of the data from WPS, which comes in typically on constant pressure levels, to model levels which are terrain following. The complication of this vertical interpolation often occurs near the ground, as shown in this sketch, where intersections of constant pressure levels, ground levels, and model levels happen. Depending on how these levels are vertically located relative to each other, choices need to be made as which bracketing levels are best used for vertical interpolation, as indicated by these vertical lines on the sketch. Surface level data coming from an external model may have more uncertainty than the atmospheric analysis or forecast. If we trust the data, we should use it in the vertical interpolation, and this can be controlled by namelist variable useSurface. If the incoming data doesn't have surface level data, then the variable should be set to false. For the vertical interpolation in the atmosphere, linear, quadratic, which is the default, or cubic interpolation orders are available. If the incoming data has coarser vertical resolution, usually higher order in vertical interpolation is better to use. There are other things we can control on how to do vertical interpolation near the surface. For example, do we want to use constant pressure levels below the model ground in higher order vertical interpolation? Should we fill the first model level with surface data coming from another model? We can also choose how many model levels the surface data can impact in the vertical interpolation. If we have model levels that are below the lowest level of the incoming data, we may need to choose an extrapolation method to get data reasonably onto those levels. This slide shows the options we can change to modify the reference state of the model atmosphere. We may remember from the dynamics talk that it is advantageous to write the model equations using perturbation variables to reduce the truncation errors in the horizontal pressure gradient force calculations and the machine running errors in the vertical pressure and the buoyancy calculations. Therefore, we need to define the base or reference state of the model atmosphere, and the perturbation variables are obtained then by subtracting the base state from the full atmospheric state variables. The base state can be defined using temperature at the sea level. If we only use the single variable to define the base state with an assumed lapse rate, the base state temperature can become very cold at higher model levels, as shown by the straight black line in the sketch here. Hence, we introduce two other parameters. One of these is the temperature of the isothermal layer, which happens in the lower stratosphere. If you would like to use even higher model top, you can improve the base state by assuming the reference temperature will increase slightly in that layer. These three parameters alter the reference state from the straight line to the green profile in the sketch, which will generally reduce the perturbation fields when solving the model equations. In the talk about running the WRF model, we said that when we are just starting, it is best we leave to program real.exe to compute the distribution of the model vertical levels. When we are ready to fine-tune these vertical levels, the options listed on this slide can be used. A good distribution of vertical levels means that delta z, or the thickness of the layer, change smoothly from the surface to the top of the model. The first option, auto levels opt, chooses the method to compute the vertical levels. Option 2 has become the default since version 4. The next two options are the stretching coefficients for the lower and upper atmosphere. Usually the coefficient for the lower atmosphere is slightly larger than those in the upper atmosphere. We can also define the thickness of the first full model layer and limit the maximum thickness anywhere in the vertical. This plot shows how delta z varies as a function of levels. The purple line, green and the blue ones all have 45 vertical levels. The purple line shows delta z as computed from the old method, the option 1. We can see that there is a big jump of the value at level 11. The green and the blue lines show delta z varies with different stretching coefficients using the new method. Both have delta z varying more smoothly with levels. The orange line shows a distribution of more levels, in this case 50 of them, that have higher vertical resolution in the lowest 30 levels, and almost a constant delta Z layer can be achieved near the model top. When we try to adjust these parameters, run real.exe only for one time period, and examine the printout and see if the levels are good enough. We may need to do a few iterations to get the levels we want. The next couple of slides show some different ways to handle model output. We are familiar with history interval option from the running the model talk. We may remember the time unit for this variable is minute. If we would like to use different time units, the model has the option to do so, as shown in these two variables. We can use history interval in hours or in seconds. The next two variables let you decide when we would like the model to start writing history files. If we know we are not going to need the model output for a certain period of time near the beginning of the model run. There are a few more like this showing here, and you can find them in the registry files. We may remember that typically, when we run the model, we expect to have the input and the output files available in the working directory. But the model does allow us to read and write files in a different directory, like what shown here. The directory name can be specified in the in-name and out-name variables. The syntax to identify domains and the time of the files should be set exactly like what they are showing here. Again, look for these options in the registry file. When we run the model, the standard history output data is written to WRF file in output stream 0 and at the frequency set by history_interval. But we can write selected model fields to different streams and at different output frequencies, provided that these model fields are declared as state variables in the model registry. We can do so by modifying the attributes in the registry files, such as registry.em_comment, which contains most of the variables used in the model. An example to output model rainfall produced by cumulus scheme, rain-C, and the macrophysics scheme, rain-NC, is shown on this slide. Normally, the field goes to history file in stream 0 by default, and we are changing it to also go to stream number 3. This is done by adding 03 to the 2 lines in the registry file. We then need to add some options in the namelist file to define the output file name, output frequency, and how we want the files to be split, and as well as the file format. Here, because we made changes in the registry file, we need to recompile the model starting with clean-a option. Then we can run the model and obtain these fields in a different output stream. You may notice that the method described on the previous slide requires a full model recompile, which may not be that convenient when we are just doing some quick test of model development. As it turns out, there is an equivalent runtime option we can use to do the same. This is described on this slide. First, we prepare a text file, name it, and we then add the toNamelist to the namelist.input file in the record time control. The option ignore I/O fields warning means exactly what it says. It will ignore any error reported due to the execution of this option. For example, the field you wanted to output did not exist somewhere. The syntax of the text file needs to be strictly followed. In the example shown here, it shows how to add the two rainfall fields to the history stream number 3. Then we will need those options to output the fields in the namelist file, as well as we did in the previous slide. With all these steps, we can now output these model fields to another file without need to compile the model. While this option is certainly convenient, a caveat is that it is not efficient for production runs. For production runs, it is best to modify the registry file, compile it once, and then use it in your production runs. We will save computer time using the registry file method. Another useful note here is that if we are going to use any output streams, all 4 associated namelists, outName, interval, frames per, and I/O form needs to be set in the namelist file. Though a generic file name does exist if outName is not set. The next 2 slides describe how physics options can be set in a namelist file as a suite rather than the individual members. The physics suites represent well-tested physics options, and the model currently have 2. These are tropical and Akana suites. The tropical suite is intended for tropical and subtropical applications, and the Akana suite is for mid-latitude continental applications. The individual members of the physics options for the respective suite are listed on the slide. We can modify the suite by overwriting any of the individual members. For example, to turn off the cumulus option in a fine domain where cumulus scheme should not be used, we can set physics suite to tropical and add CU physics option in the namelist. We can then set the value to -1 for any domains that uses the suite choice, and set the value to 0 to turn the option off, like the one showing on the left-hand side of the slide. If we want to replace one or more of the options in the suite, simply add those options and set the correct value. The next 2 slides list options used mostly in long simulations, simulations longer than 1 or 2 weeks, and they are covered in physics talk. Here we will mention how the input file is generated for one of the options. To use the SST update option, it requires an additional input file. So we must set this option before we run program real.exe, and running the program will create an actual file called WRF-low-imp. This file contains the data such as SST, CIs, monthly vegetation fraction, and so on, used by the SST update option. If we run ST-WRF, we should have this file for each of the domains. In addition to setting the SST update option, a couple of options also need to be set in order for the model to recognize the data, and these are in-name, interval, and I/O form for auxiliary input stream number 4. Most of the options showing on this slide are covered in the physics talk. The one that may not is the last one on the list, spec_exp option. This is used together with the width of the lateral boundary zone, spec BDY width. Rather than reducing the forcing data linearly from the outmost row and column to the end of the boundary zone, this option offers a fast decaying function that reduces the impact of forcing data, as shown by the brown curve in the small sketch on the slide. This is shown to work well with wider boundary zone and with coarser resolution forcing data. The next option we will cover is the adaptive time step option. Adaptive time step is relative to a fixed time step, which we've learned to use before. By definition, the adaptive time stepping means that the model will use variable time steps, and the size of the time step is determined by the model's stability at any time during a model integration. This is a way to allow the model to use a larger time step when the model is stable, and a smaller one when it needs to. It is good to use this option in a real-time application where we want the model to finish in the shortest amount of time. A caveat with this option is that the option has not been tested with every other option in the model, so it may or may not work with all of them. The advantage of using adaptive time stepping is illustrated on this plot, which shows the wall clock time taken to run a configuration of the model twice a day using a fixed time step versus adaptive time steps during a 2-month period. The right line shows the wall clock time taken by this model configuration when using a fixed time step, and that time is about 79 minutes per run. The blue curve shows the wall clock time taken by this model using adaptive time steps, which average to about 60 minutes during the 2-month period. In general, it saves computer time when adaptive time steps are used. To help us to have some control over the variable time steps, we have these options. Use adaptive time step turns this option on. Set to output time allows the model to write output at the interval set by the user, even with variable time steps. Target CFL sets the model stability criteria against which the time steps are evaluated. Max step increase percent sets the maximum percentage change allowed for time step to increase or decrease at any one time. The max and min time step sets the bounds for the maximum and the minimum tap steps to avoid any wild swing of the variable time step. Set these options carefully and use the option with care. The next option we're going to talk about is the digital filter initialization option, or DFI. What is DFI? DFI is a way to use a low-pass numerical filter to remove noise or imbalance from the model initial state. Why is the model initial state not balanced? The imbalance can be introduced into the model by using the data simply from a different model, by interpolation, both horizontal and vertical, and by introducing a terrain that is different and typically has higher resolution than where the atmospheric data is produced. It can also be introduced by objective analysis and the data assimilation if those steps are used to prepare models' initial conditions. Why is the imbalance in the model initial state bad? The imbalance can generate spurious gravity waves in the early simulation hours, which could cause erroneous vertical motion and precipitation, and even numerical instability. As this imbalance affects short-range weather forecast more, using this technique is useful for improving 1 to 6 hour model forecast. If we are more interested in longer forecast, the model is capable of sort this out and produce balanced solution for later simulation hours. A benefit with using DFI is that the technique can help construct consistent model fields that do not exist in the initial conditions, because a short simulation window is involved. For example, vertical motion and cloud variables. It may also help reduce the spin-up problem in the early forecast hours and help with cycling using data simulation. DFI is executed as part of the model integration with an option to stop after just the DFI. We mentioned model imbalance before, but how do we measure it? It turns out a good measure of model's balance is the surface pressure tendency in the model. That is, the rate at which the surface pressure changes with time. This plot shows the evolution of the domain averaged surface pressure tendency with time when the model is initialized with GFS data and with and without DFI. We can see that all pressure tendencies settle down after several hours of model integration. However, immediately after the model start, the pressure tendencies change rapidly, and this is an indication that the model is not in a balanced state. We can also see that if we start the model with higher resolution GFS data, the quarter degree GFS, as represented by the red curve here, rather than the 1 degree one, as represented by the green curve here. There is a dramatic improvement in the adjustment the model has to make in the early forecast hours. The plot also shows that the DFI is very effective in removing this initial adjustment and brings the model into a balanced state right from the start, as shown by the black line on this plot. There are 3 ways to do DFI in the model. The first is the simplest, called the digital filter launch. This option runs DFI during a period of the model integration, and then launch the forecast from the middle point of the DF window. This option will not alter the model initial state. The second option is called diabatic DFI. The option first integrates the model backward, adiabatically, and then integrate the model forward diabatically, which means physics is activated, and run DFI during this forward integration. Forecast is then launched at the original model start time. This option can alter the model initial state. The third option is called twice DFI. This option differs from the second option by doing filtering during the backward integration as well as the forward integration. Like the second option, this one will change the initial model state too. Some options to control DFI are listed on this slide. A typical DFI window is about 30 minutes to 1 or 2 hours. With the 30-minute window applied to models with a few kilometer grid sizes, and a 1 or 2 hours window for models of coarser resolution. More information can be found in the WRF tech note, which is available online. Next, we are going to talk briefly about the stochastic parameterization schemes in the model. The basic idea behind this is that because we are solving model equations with finite resolution, there's always subgrid scale processes that are not well represented in the model, whether it is in dynamics or physics. Hence, a random or stochastic component should be considered. The way this stochastic component is added to the model is throughout the model integration at every model time step. The method includes SCAPS, stochastic kinetic energy backscatter scheme for rotational winds and temperature, the dynamic part of the model. SPPT, stochastically perturbed parameterization tendencies for some physics schemes, and SPP, stochastically perturbed parameterization schemes. The last one adds perturbation to parameters inside a physics scheme. Only a group of selected physics has this option, but the framework is there to be employed by other physics options. In addition, perturbation can be added to the boundary data. More information can be found on the listed website. The WRF model has a tracer option, which is activated by namelist option tracer opt. There are 8 tracer arrays by default, but more can be added in the registry. The simplest way to initialize the tracers is to set them in program real.exe with the initial values. Code can be added to do continuous releases, like the example showing in the how to use the WRF registry talk. This image shows a tracer continuously released from the Fukushima site at some time into the model integration. Note that the tracers are not impacted by physics in this simple implementation. The WRF model also has a trajectory option. It is activated by namelist traj opt, and the number of trajectories can be set too. In addition to the locations of each trajectory, one can obtain the atmospheric variables along the trajectory. Hence, this can be a very powerful diagnostic tool. The trajectory start locations are specified in an additional input file, and the full documentation of this option can be found in the file showing on the slide. In the next set of slides, we're going to cover some special output options. The first of this is to output precipitation variables in a time interval. The precipitation fields in standard model output, rain-C and rain-NC, are accumulated variables from the model start time. Hence, sometimes it is convenient to output these variables in a time interval. The interval is set by namelist variable PRECACCDT, and the time unit is minute. This is also the variable to activate this option. The option writes 3 additional 2D fields to WRF out file, and these are precipitation produced by convective parameterization, by microphysics. The snow here is also from microphysics. The second output option is to write out a selection of model fields on constant pressure levels. The standard model output is on model levels, which is terrain following, which makes the viewing of the data complicated at times. This is activated by setting pleft diag equal to 1, and we can set the number of and the pressure levels themselves for output. And the variables in this output will be more familiar to us, such as temperature, relative humidity, and the geopotential height. The output goes to output stream 23, and the I/O variables associated with stream 23 need to be set in the namelist file. The next option is similar to the one for pressure levels, but this one is for height. Again, we can set the number of and the height levels themselves for the data. The data also goes to the output stream number 23. The third option is to output actual meteorological fields instead of model fields such as perturbation potential temperature on model levels. So far, we have this list of fields available, which include mean sea level pressure, temperature, wind component relative to Earth, and total surface precipitation, and so on. This option is activated by diag's NWP variable, and the data goes to output stream 1. The fourth option is to output actual diagnostic fields useful for severe convection forecast. It includes maximum helicity in the layer, maximum vertical motion in updraft and downdraft, maximum grapple in a column, and so on in between history times. The output is activated by setting option NLP diagnostics, and the data goes to standard history file. This option lets us output simulated radar reflectivity from most of the available macrophysics options, using parameters from the respective options. The option is activated by setting do radar ref equal to 1, and the output field goes to standard history file. If we are interested in more diagnostics for weather forecast, we can activate a suite of AFWA diagnostics. AFWA stands for Air Force Weather Agency, and these diagnostics were contributed by the agency. The diagnostics include many fields a forecast might be interested, such as cloud cover, cloud ceiling, visibility, and so on. A full list can be found in the registry file, registry.afwa. The data goes to standard history file as well as output stream 2. The model also has some additional output targeted for climate runs. One of these is output diagnostics. This option computes maximum, minimum, time of the maximum and the minimum, the mean and the standard deviations of 8 surface variables listed on this slide in history output interval. And the output goes to stream number 3. Another option for climate diagnostics is the option to compute averages of the surface meteorological variables, surface fluxes, and radiative fluxes at the bottom and the top of the atmosphere over an interval set in the name list. The option is contributed by RASM group. RASM stands for Regional Arctic System Model. The interval could be daily or monthly. In addition, there is an option to compute diurnal averages, but this is only for monthly averages. More information can be found in the README file, and the field can be found in the registry file. Data goes to output stream 5 and 6. The final output option is aimed for downstream transport model, and the option name is listed here, where EM is just another name for Air W. This option computes the time-averaged, mass-coupled advective velocities of U, V, and W, and output them according to history output frequency, and the data goes to standard history file. One last point about doing more diagnostic calculations in the model. Often post-processing programs are not able to run using multiple processors. Hence, computing these diagnostics in the model can be efficient because it takes advantage of model's parallelism. This slide shows the 2 options for I/O quilting. The basic idea here is that when the model uses many processors, a small percentage of the processors can be set aside for working on I/O only. These processors would gather data from each processor, put them together, and write the data out. This is only needed when the model's grid numbers is huge, and we have access to hundreds or thousands of processors. This helps to improve overall model performances, even though a set of the process is not used for computing. There are other ways to improve NetCDF writing. One of these methods is to use pNetCDF. However, this would require additional library at the compile time. Another way is to make use of the compression option in netcdef4, which has become the default since the WRF Model 4 release. And finally, setting IO form history equal to 102 rather than 2 will allow each processor to write the data on that processor. This is by far the fastest way to write data, but a post-processing step is required to put the individual files together. The final option we will cover is time series output. In contrast to other output from the model, which are binary, the time series output is in text format and is written to a file named such as this. Here the prefix is usually a location name. It outputs 14 surface variables at every model time step. Variables like 10-meter wind, 2-meter temperature, and water mixing ratio, and the precipitation, and so on. The data is written one location per file per domain. In addition, we also get time series output of lower atmospheric profiles of wind, potential temperature, and so on. Here we have one variable per file, per location, and per domain. The time series output is activated by the presence of a file called tslist in the working directory. This file has the list of names, the locations, and the prefix of the file names. If we need more than 5 time series, we need to add namelist max ts logs in the namelist file and set the number. A template of this tslist file can be cut and pasted from the readme.tslist file in the run directory. Since the output are text files, we can open and read the data. The time series output of any variable can be plotted using graphic tools like NCL. A sample plot of 2-meter temperature is showing here. We have reached the end of this talk, and we have covered a number of options that may be useful to us at some future time. More information about namelist options can be found in various places in the code, as well as in the tech note and the user's guide. Thank you for listening, and please prepare questions for discussion during the actual tutorial.